Okay, so we're going to start our study of linear algebra in earnest. If you've studied things before, if you've done some algebra before, I need to warn you that we're starting with the new part first. Now, this is unlikely to be something you would have seen in your high school classes, and that's just the nature of the course. We're going to start with the new concepts first, the idea of vector spaces. It's important to do a lot of exercises, right? Because these are new concepts. You have to take the time to learn the definitions. One thing that I will mention is that when we introduce vector spaces first, we expect you to only be able to use the ideas that have been developed up to now. So if you've studied linear algebra before, you might have learned how to solve linear systems, for instance, or perhaps even talked about eigenvalues and linear transformations. In this version of the course, we haven't introduced these concepts up to now, right? And so very often we will have to sort of do some fancy footwork, perhaps wave our hands around to say, well, if we knew how to solve linear systems, this is what we would do. And you might think to yourself, but I know how to solve linear systems. Why don't I do this? Like, perhaps you do, but we haven't introduced it in the course yet, right? So the way this course is set up is whenever we produce results, they can only be proved with stuff that we have introduced up to that point. Right, so you can't sort of go and fish out something that hasn't yet been introduced, even if you might have learned about it in a previous course. That's the nature of the game. In general, vector spaces tend to be a little bit more confusing for students. And so we're starting with those up front because we think it's an important concept, and the more time you have to practice and the more time you have to absorb the ideas, the better it is for you in the long run, the more likely you are to remember them. Comes final exam time. We'll talk about the basics of what vector spaces and subspaces would be. Then we'll discuss a very important concept, the concept of linear independence, and its opposite concept, linear dependence. We'll talk about the dimension of a vector space, and that will be enough to take us through to the next topic, the next chapter, which will be how we actually solve linear systems. So it's pretty easy in general to extend the algebra of 2 space and 3 space to n space. What we're interested in here is to find mathematical objects that behave like n space from an algebraic perspective. It turns out that there are such objects. We call them vector spaces, and they do not have to be vectors as in geometrical vectors, n tuples, right? A collection of n numbers like this. In order to really define these objects, these vector spaces, we need to introduce a number of concepts. We'll talk about spanning sets, we'll talk about linear independence, and we'll talk about bases and dimension of vector spaces. So these are all concepts, these 3 things here for sure, or 4 things. You need to know what they mean, and you need to know how to verify, how to implement, apply these concepts. There's more, but at the very least, these ones. All right, so arrows in 2 space and 3 space, we can generalize that to n tuples and coordinates in n space. We call them vectors, as I said, even though they're not really like arrows in space anymore. There are a few issues associated with those, like how do we define a line or a plane in higher dimensional spaces? How can we actually describe them? It's not a bad idea then for us to sort of step back a little bit and say we're just not going to be talking about n space. We're going to talk about vector spaces in general. things that behave like 2 space and 3 space does with respect to a vector addition and a scalar multiplication. So if we define a bunch of objects and then we define an operation that behaves like vector addition and another operation that behaves like scalar multiplication, then we have hopefully something that does behave an awful lot like n space does, right? All these spaces have things in common. The commonality is these properties, and then we call them vector spaces, because when we can say something about one vector space in a general setting, it typically also applies to other vector spaces. Vectors don't have to be these arrows, these geometric arrows, or even n-tuples. But vectors are things that behave like arrows and n-tuples from an algebraic perspective. We'll consider a set V of things that we call vectors, and it has an operation which is called vector addition, and I write it here like this. I use the plus sign because it's going to behave like a vector addition, and I want to sort of keep that in mind, that some of the properties are there, but it's not necessarily the plus that you're used to. We say it's a function from V cross V into V. This cross is not the cross product. What it's telling us is that plus, whatever this operation here is, takes a vector and a second vector and gives us a third vector, which by abuse of notation we often also write like this. So the cross here is telling us that there are 2 different inputs to this function. If you wanted to, you could think of r squared as r cross r. There are 2 coordinates in order to get a point in the plane. Scalar multiplication is a function which we denote by the dot. Often when we write down scalar multiplication, we will not write the dot down, or we'll just have the scalar and then the vector itself, and we understand that this is a vector that has been stretched, whatever that might mean, right? But formally, when we write that the scalar multiplication is a function of r cross v into v, what it means is that it takes a scalar k and a vector u, and it outputs something like this, which is also a vector. All right, so again, the cross here is telling us that there are 2 inputs that go into this operation, and the result is a vector in V. The combination of the set of vectors, whatever these might be, together with the sum and the scalar multiplication, we call that a vector space as long as it follows or satisfies 10 axioms. The first one is an axiom of closure. In fact, there's more than one closure axiom, but the very first axiom is one of the closure axioms. It says that V is big enough. So if you were to take a vector in V and another vector in V, and you add them up together, whatever the addition is, the result is still a vector in your space. You haven't left the space, right? So it's big enough, and big in the sense that if you have a complex number and you add to it a complex number, the result has to be a complex number. It can't be something other than a complex number. You can say, it could be a real number, sure, but a real number is also a complex number, right? It's a complex number with 0 imaginary part. So we write it like this. If U and V are vectors, then their sum is also a vector. And when I say are vectors, what I mean is that they belong to the set V of vectors. They belong to that universe that we are considering. Another closure axiom is that scalar multiplication doesn't take your vectors out of the space in question. So if you have a vector and you stretch it, you're still in the space. You haven't left the space. Formally, we would say if U is a vector and C is a scalar, then the scalar multiplication, the scalar product C times U, is still a vector. It's still in the space. There are two existence axioms. Basically, you need to be sure that there's a special vector, the zero vector. Again, this is the bold vector, or the zero with an arrow on it, that has the effect that when you add it to any other vector, you haven't changed anything. And for every vector in your space, you can find a negative of that vector, a reciprocal, which is basically -1 times that vector, that is going to have the property that U plus the negative of U gives you the zero vector. So in essence, you can always reverse a vector. And then there are 6 properties that are of an arithmetic nature. So it makes sure, or at least these axioms make sure, that the sum and the scalar product behave as they should, right? If we're going to call them a sum and a scalar product, they should at least have these properties. They should, the sum should be commutative. Whether you add U and V together or V and U, you should get the same result. Well, we've seen an example of an operation that wasn't like this, right? The cross product on R3, U times V is not the same as V times U. So the cross product does not behave like a sum should. The vector sum is also associative. So U plus V plus W, you can write it as U plus V plus W, or U plus V plus W, and then you get the same answer. Again, the cross product is not associative. So it's not a given that an operation is going to be commutative or associative. You know, it depends on the actual operation. The scalar multiplication on a sum, well, you can distribute the scalar. So C of U plus V would be CU plus CV. Very important, C of U plus V, not the same thing as CU plus V, unless C was equal to 1 in the first place, right? You can also distribute a sum of scalars over a vector, so CU plus DU. The plus that shows up here in C plus D is not the same plus as the plus that shows up here. When I write U plus V, I'm talking about the plus, the addition that is defined for vectors. When I write C plus D, I'm talking about the regular plus, the plus that's defined for scalars, for real numbers. You have to be able to recognize that these are different operations, even though they have the same notation. You can also associate the scalars differently. C of D times U is the same as CD times U. And finally, there is that special relationship. If you multiply any vector by the scalar 1, then you get the vector itself. Again, that's not a given, right? Your scalar multiplication has to sort of work that way. Anything that satisfies these 10 properties, these 10 axioms, is a vector space. Here are some examples. R, 2 space, 3 space, n space, all of these are vector spaces if you use the usual operations. And that shouldn't be surprising, right? Because we use these spaces as the prototype for what a vector space should be. Like these operations we see here, certainly 5, 6, all the way up to 10, we've basically said, well, this is how n space behaves, and I want something like this. The other ones are less obvious, but they're also properties of n space. If you look at the set of linear equations in n variables, so something that would look like this, for instance, would be part of that set. x1 minus 2x2 plus x5 is an equation. Let's make this equal to 3. So this equation here, that's an equation in 5 variables. You can think of that as a vector, right? Because we can add equations together. We did one example when we were trying to solve a linear system in the previous chapter. So an equation can be a vector as long as you have a way to add equations together, and as long as you have a way to multiply an equation by a scalar, and as long as there's something that plays the role of the zero equation. It would probably be something like this here. Right? If that's the case, and all of the properties of vector spaces are satisfied, then the set of all linear equations and n variables would be a vector space. And in fact, it is. But you have to be sure to have defined what it means to add equations together and to multiply an equation by a scalar. This isn't something we're going to do in the course, but there's a little bit of this in the book Vector Spaces first, if you want to read up more about it. The set that only contains one vector, which is to say the zero vector. Now, I want to be careful about this notation. This is not the same thing as saying that the set is empty. It's not the same thing at all. It's also not the same thing as just the zero vector alone. No, it's the set that contains the zero vector. This set is a vector space, right? Because there's only one vector in the set. Here's how you add it with itself. 0 plus 0 is 0. You can multiply 0 by any c, you still get 0. And then all of the other properties follow because there's literally only these two things to work with. That's a vector space. It's a special vector space. We call it the zero vector space. You're going to wonder why the zero vector space is even worth talking about. Well, it's typically one of the n cases whenever we show things about vector spaces. So it's not bad to have this lower limit, so to speak. The empty set, which is to say something that contains nothing, is not a vector space, right? Because in order to be a vector space, there has to be at least one vector in there that's special, the zero vector. And the empty set contains nothing. I remind you that the empty set and the zero space, they're not the same thing. They're different things. Here's an example which is perhaps less trivial than everything else we've seen so far. So I'm going to look at a subset of R2, right? If I look at V here, it is the set of all two vectors, so there's two components, that basically has a first coordinate be half of the second coordinate. Let me trace the graph of what that would look like, right? This is R2, 2 space, and V is basically saying if x is 0, x should be, y should be 0. If x is 1, y should be 2. What we have here is, roughly speaking, the line 2x. So we're looking at the points that are on this line. So for instance, this point here, not in V. This point is in V. So is this point right here. So is this point right here. So all of these are vectors of R2, but they are restricted to the line y equals 2x. So is that a vector space? Well, we need to verify that it satisfies the 10 properties. Is it closed under addition? If I take a vector on that line, so an arrow whose point head falls on that line, and some other arrow whose head also falls on that line, and both of these arrows start at the origin, is it the case that when I add them together, the result will also be an arrow that falls on that specific line? How do I prove this? Well, look, in the general case, it's not enough to pick examples. I could pick examples. I could say, well, look, definitely the point 1, 2 is in V, and definitely the point, I don't know, 3, 6 is in V. That's what it means to be in V, right? The second coordinate is twice the first one. If I add them up together, I get 3 plus 1 and then 6 plus 2, and that's equal to 4, 8. And that's also in V because the second coordinate is twice the first one. But that's not a proof. That's an example. I've illustrated that the property at least holds for some vector. Now, the fact that I picked vectors at random and it worked is a good indication that it is probably true that V is closed under vector addition, but it's not a guarantee, right? I have to go and prove it. The example also sort of, gives me an idea as to how I might go about proving it, but the example on its own, not a proof, not sufficient. What does a proof look like? Well, look, you're supposed to show that whenever you start with two vectors in V, the result is also in V. So let's say you start with two vectors in V. What do you know about U and V? If they are in the set V, big V, then their second coordinate has to be twice as big as the first one. I don't know what the second or the first coordinates would be, but all I know is that the second one is going to be twice as big as the first one. So U, the first vector, might look like x2x. And V, the second vector, might look like y2y. You might call them something else. You could say s2s and t2t. Or you could also write those as half of x and x. Doesn't matter how you write it, as long as the second coordinate is twice as large as the first one, and as long as you don't use the same description for both of those, right? Because they're supposed to be general vectors, not specific vectors. So, okay, so we know what a u would look like in general. We know what a v would look like in general. We don't know what x and y are specifically, but that's because we haven't picked a specific u and v. If we add them together, according to the rule for vector addition in two-space, because these are also two-space vector, not only are they in V, but they're also in R2, in two-space. And it is the vector addition from R2 that is inherited by V as a subset of R squared. So how do we actually add? We just add them component by component. So U plus V would be the first components add x plus y, the second components add 2x plus 2y. Now the question is this thing here, this result, is it in V? Well, we need to know the condition, the membership condition. How do we know if something is in V? Something is in V if the second coordinate is twice as big as the first one. So typically at this point we have to do some simplification. Right, so here we apply the definition of the sum, and then we do some simplification to see if we can rewrite the result in a form that makes it clear that it belongs to V or that it does not belong to V. The condition for this specific V, that's going to change from one space to another, but in this example, the condition is that the second component is twice as big as the first. And it turns out that, yeah, I can basically take out a factor of 2 here, and I end up with x plus y for my first component, and my second component would be twice x plus y. So, the first component is half of the second component, or the second component is twice as big as the first. And so, this result, u plus v, is indeed in the set V, because it is of the form Z to Z, where the Z happens to be x plus y, whatever x and y would have been. See, we don't need to specify that U is 1, 2, and that V is 3, 6. This works for every possible choice of U and V. If we wanted to prove it to be true for every U and V separately, it would take, well, we have to try it for every pair U and V, and there's like infinitely many of those. We wouldn't be able to do it. But with this proof, we've managed to hit all of the vector sums simultaneously. We do the same thing now, closure for scalar multiplication. So if I start with a vector in V, let's call it U, and I start with a scalar C, the product of C and U should still be in this set V. So if U is in V, I know its second coordinate is twice as big as its first coordinate. So let's say we call it x2x. X could be anything. The scalar multiple of C and U inherited from the fact that these are two vectors would be you multiply each coordinate by C. So the first coordinate becomes C times X, and the second coordinate becomes C times 2X. And according to the properties of multiplication by real numbers, which C and 2 both are, this is the same thing as twice times CX. And so what we have is that the second coordinate is indeed twice as big as the first, so this product CU is indeed in V. So the space that we've defined, that line, slope 2 through the origin in R2 is closed under vector addition, and it is closed under scalar multiplication. That's a pretty good sign. This is usually where problems arise, if something is not going to be a vector space. But it's not enough. There's 8 other properties that we need to show. Well, first of all, we need to show that there's a special vector, the zero vector. The only reasonable candidate for what that zero vector should be is, well, the origin, the vector 0, 0. That vector is going to be in V, if and only if the second coordinate is twice as big as the first coordinate. And that's indeed the case, right? The second coordinate is twice as big as the first one because 2 times 0 is actually 0. So the 0 vector is in V, which is good, but that's not the only thing we need to know about the 0 vector. That 0 vector actually has to act as a 0 vector would, which is to say that when you add the 0 vector to the space, it doesn't, to the vector in the space, it doesn't actually change the vector. 0 plus U should be equal to U. It is, because you're adding 0 to each of the components. So yeah, there is a 0 vector. It's in the set V. It behaves as the 0 vector would or should. We also need to show that there's an inverse. Well, is there an inverse? If you take the vector U, it has, and it's in V, it has to be so that the second component is twice as big as the first. So it looks like x2x, great. What is the inverse going to be? What's the negative going to be? What's the reciprocal going to be? The only natural candidate here would be minus x minus 2x. And sure enough, x2x plus minus x minus 2x, that does give you 0, 0. So that's not surprising. I mean, we built it that way. But the thing that you have to check now is that this thing that when you add to it, it gives you 0, 0. You have to check that it is indeed in V. Otherwise, you're adding something which might not be in V in order to get 0, 0. But it is the case. Minus 2x, the second coordinate, is twice as large as the first coordinate. So yeah, we have negatives. We have inverses. We have reciprocals. The other properties, 5, 6, 7, 8, 9, 10, we know they hold because they actually work for any vector in 2 space, not just the ones that are in V. So we've actually managed to show all 10 properties. This set V is itself a vector space. It's basically a copy of the real line that has been rotated in R2. If R is a vector space, it's not surprising that this line would be a vector space, because it's basically the same thing as V.